Hello and welcome back. Today we are starting a brand new chapter. Chapter 1 of Class 11 Physics, Units and Measurement. Now, before we dive in, let's think about why this chapter even exists. Physics is a science of measurement. Whenever we say something like, the speed of light is very fast, or this table is long, we are being vague. Physics doesn't like vague, it likes numbers. And every number in physics needs two things, a magnitude and a unit. Without a unit, a number is meaningless. If I say the length of this rod is 5, you'd immediately ask, 5 what? 5 centimeters? 5 meters? 5 feet? That's exactly why this chapter matters. It lays the foundation for every single measurement you'll make in physics from here on. By the end of this lesson, you'll understand what physical quantities are, how we classify and measure them, what the SI system is, how to handle errors in measurement, how to work with significant figures, and how to use dimensional analysis to check equations and derive relationships. Let's get started. Let's begin with the basic building block, the physical quantity. A physical quantity is anything that can be measured, like length, mass, time, temperature, or electric current. Every physical quantity is expressed as a number followed by a unit. For example, when we say a person's height is 1.7 meters, 1.7 inch is the numerical value, and meter is the unit. Physical quantities are broadly divided into two categories. First, fundamental or base quantities. These are quantities that are independent of each other and cannot be derived from any other physical quantity. Examples include length, mass, time, electric current, temperature, amount of substance, and luminous intensity. Second, derived quantities. These are quantities that are obtained by combining fundamental quantities using mathematical operations like multiplication or division. For example, speed is length divided by time. Area is length multiplied by length. Force is mass multiplied by acceleration. All of these are derived quantities because they're built from the fundamental ones. Now that we know what physical quantities are, let's talk about how we measure them. Using units. A unit is basically a reference standard used to express a physical quantity. Historically, different countries and regions use different systems. The CGS system based on centimeter, gram, and second. The FPS system based on foot, pound, and second. And the MKS system based on meter, kilogram, and second. This created a lot of confusion in scientific communication across the world. To solve this, in 1960, the international scientific communication across the world. To solve this, in 1960, the International Unité. This is the system used almost universally in science today. The SI system has 7 base units corresponding to the 7 fundamental quantities. Length, measured in meter, symbol m. Mass, measured in kilogram, symbol kg. Time, measured in second, symbol s. Electric current, measured in ampere, symbol A. Thermodynamic temperature, measured in Kelvin, symbol K. Amount of substance, measured in mole, symbol mol. Luminous intensity, measured in candela, symbol CD. Each of these base units is now defined in terms of fixed values of fundamental constants of nature. For instance, the second is defined using the vibrations of a cesium-133 atom, and the meter is defined using the distance light travels in a specific fraction of a second. This makes these units incredibly precise and reproducible anywhere in the universe, not tied to any physical object kept in a vault somewhere. In addition to these 7 base units, there are 2 supplementary units: the radian for measuring plane angles, the steradian for measuring solid angles. All other units, like the unit of force, the Newton, the unit of energy, the joule, or the unit of pressure, the Pascal, are derived units built from combinations of these base units. Let's now look at how we actually measure these fundamental quantities in practice, because the range of sizes in the universe is mind-bogglingly vast. Length can range from the size of a proton, about 10 to the power of minus 15 meters, all the way to the size of the observable universe, around 10 to the power of 26 meters. Obviously, you can't use the same method to measure both. For everyday lengths, we use rulers and measuring tapes. For very large astronomical distances, we use methods like parallax, where we observe an object from two different points and use the angle of shift to calculate distance. For very small distances, like the size of molecules, we use specialized techniques involving electron microscopes or X-ray diffraction. Mass also ranges enormously. From the mass of an electron, about 10 to the power of minus 30 kilograms, to the mass of the known universe, around 10 to the power of 55 kilograms. Everyday masses are measured using a common balance. Very small masses, like those of atoms, are measured using a mass spectrograph, which uses electric and magnetic fields to deflect charged particles based on their mass. Time is measured using clocks. Traditionally, mechanical clocks and pendulum clocks were used, but today the most precise time standard is the atomic clock, which uses the extremely regular vibration frequency of cesium atoms. Atomic clocks are so precise they may lose or gain only about 1 second in many thousands of years. No measurement is ever perfectly exact. Every measurement has some degree of uncertainty. This brings us to two important and often confused terms: accuracy and precision. Accuracy refers to how close a measured value is to the true value. Precision refers to the resolution or the smallest measurable change, basically how consistent repeated measurements are with each other, regardless of whether they are close to the true value. Here's a simple way to remember the difference. Imagine shooting arrows at a target. If all your arrows land close together but far from the bullseye, you're precise but not accurate. If your arrows are scattered around the bullseye but not clustered together, you're accurate. Accurate or arrows are scattered around the bullseye but not clustered together. You're accurate on average but not precise. Ideally, we want both. Now let's talk about errors, the difference between the measured value and the true value of a quantity. Errors are classified into a few types. Systematic errors are errors that consistently occur in the same direction, either always too high or always too low. These arise due to issues like faulty instruments, imperfect measurement technique, or environmental conditions that aren't accounted for. Because they are consistent, systematic errors can often be identified and corrected. Random errors occur irregularly and unpredictably due to unknown or uncontrollable factors, small fluctuations in conditions, or limitations in the observer's ability to read an instrument the exact same way every time. These cause repeated measurements of the same quantity to differ slightly from one another. Gross errors arise from human carelessness, like misreading an instrument or recording the wrong value entirely. When we take repeated measurements, we usually calculate the mean value, which is the average of all measurements, the absolute error, which is the difference between each individual measurement, and the mean. The mean absolute error, the average of all the absolute errors, the relative error, which is the mean absolute error divided by the mean value. This tells us the error as a fraction of the measurement. The percentage error, which is simply the relative error expressed as a percentage. When quantities with errors are combined mathematically, added, subtracted, multiplied, or divided, the errors also combine. As a general rule, when quantities are added or subtracted, their absolute errors add up. When quantities are multiplied or divided, their relative errors add up. Because every measurement has some uncertainty, we need a way to indicate how reliable a written number is. This is where significant figures come in. Significant figures are the digits in a measured number that are known with certainty, plus one estimated digit. They tell us the precision of a measurement just by looking at how the number is written. Here are the basic rules for counting significant figures. All non-zero digits are significant. So in 247, there are 3 significant figures. Zeros between non-zero digits are always significant. In 4008, there are 4 significant figures. Trailing zeros in a number without a decimal point are ambiguous, so it's best to express such numbers in scientific notation to make the significant figures clear. For instance, writing 1500 as 1.5 times 10 to the power of 3 makes it clear there are only 2 significant figures. When performing calculations, the result should be rounded off so that it reflects the precision of the least precise measurement used. In addition and subtraction, the result should have the same number of decimal places as the term with the fewest decimal places. Now let's move to one of the most powerful tools in this chapter: dimensional analysis. Every physical quantity can be expressed in terms of the 7 base quantities raised to certain powers. These powers are called the dimensions of that quantity. We use square brackets to denote dimensions, and the base quantities are represented by symbols. Length has m for mass. Wait, let me be precise here. Length is represented by L, mass by m, time by t, electric current by A, temperature by K, theta is also used, amount of substance by N, and luminous intensity by J. For example, speed is distance divided by time, so its dimensional formula is L, t to the power of minus 1. Force is mass times acceleration, and acceleration is length divided by time squared. So force has the dimensional formula mlt to the power of minus 2. An equation that relates physical quantities using their dimensions is called a dimensional equation. Dimensional analysis is useful for 3 main purposes. First, checking the correctness of an equation. This is based on the principle of homogeneity, which states that the dimensions on both sides of a valid physical equation must be exactly the same. If they don't match, the equation is definitely wrong. Though matching dimensions alone doesn't guarantee the equation is fully correct, it could still be missing a dimensionless constant or a numerical factor. Second, converting units from one system to another. Since a physical quantity's magnitude times its unit stays constant, we can use dimensional formulas to convert a measurement from, say, CGS units to SI units. Third, deriving relationships between physical quantities. If we have a good guess about which quantities a relationship depends on, we can use dimensional analysis to work out the powers to which each quantity must be raised, as long as the relationship involves a product of powers. This method doesn't work for relationships involving trigonometric, exponential, or logarithmic functions, and it also can't determine dimensionless constants. Dimensional analysis is limited in these ways, but it remains an extremely quick and powerful check on your work in physics. Many students catch calculation errors simply by verifying that their final answer has the correct dimensions.